Welcome to our deep dive into the fascinating world of fine-tuning. Have you ever wondered what actually happens inside a neural network? Today, we are going to pull back the curtain and explore the intricate mechanisms that transform a general-purpose model into a specialized expert. Let's begin this journey into the heart of machine learning. Fine-tuning is like taking a master chef who knows thousands of recipes and teaching them to specialize in Mediterranean cuisine. The chef doesn't forget everything they know. Instead, they build upon their existing knowledge to become an expert in a specific domain. Similarly, fine-tuning takes a pre-trained model with broad knowledge and adapts it for a specific task. The model retains its general understanding while learning task-specific patterns. Understanding the difference between pre-training and fine-tuning is crucial. Pre-training is like general education, where the model learns from massive amounts of diverse data, developing broad capabilities. This phase can take months and costs millions of dollars. Fine-tuning, on the other hand, is like specialized training. It takes hours or days, requires much less data, and costs far less. The pre-trained model serves as a powerful foundation, and fine-tuning adapts it efficiently. Let's look inside a neural network to see what we are actually fine-tuning. A neural network consists of layers of artificial neurons. Each neuron receives inputs, performs calculations using weights and biases, and produces an output. These weights are the learnable parameters, the knobs that get adjusted during training. In a large language model, there can be billions of these parameters. During fine-tuning, we adjust these weights to make the model better at our specific task. During fine-tuning, we show the model examples from our specific task. The model makes predictions, and we measure how wrong those predictions are using a loss function. Think of loss as the error score. Higher loss means worse performance. The training process aims to minimize this loss by adjusting the weights. It's an iterative process. Forward pass to get predictions, calculate loss, backward pass to compute gradients, and update weights. This cycle repeats thousands of times. Let's dive deeper into the mathematics. The loss function quantifies how far our predictions are from the correct answers. Common loss functions include mean-squared error for regression and cross-entropy for classification. The gradient tells us the direction and magnitude to adjust each weight. Think of it like standing on a hill. The gradient points in the direction of steepest ascent, so we move in the opposite direction to go downhill, toward lower loss. This is gradient descent. Backpropagation is the algorithm that computes gradients efficiently. It starts at the output layer, calculates the error, and then propagates this error backward through the network. At each layer, it computes how much each weight contributed to the error. This is done using the chain rule from calculus. The beauty of backpropagation is that it can compute gradients for millions of parameters efficiently in a single backward pass through the network. The learning rate is a crucial hyperparameter that controls how big the steps are when updating weights. If the learning rate is too high, the model takes large steps and might overshoot the minimum, leading to unstable training. If it's too low, training is very slow and might get stuck in local minima. Finding the right learning rate is an art and science. Modern techniques use learning rate schedules that start high and gradually decrease, or adaptive methods like ADAM that adjust the learning rate automatically. There are several approaches to fine-tuning. Full fine-tuning updates all parameters in the model, giving maximum flexibility, but requiring significant compute. Feature extraction freezes most layers and only trains the final layers, which is fast but less flexible. Layer-wise fine-tuning gradually unfreeze layers from top to bottom. And parameter-efficient methods like LoRA add small trainable modules while keeping the original model frozen, offering a great balance of performance and efficiency. Fine-tuning is a form of transfer learning. The idea is simple but powerful. Knowledge learned from one task can transfer to another. A model trained on millions of images learns to detect edges, shapes, and textures. These features are useful for many vision tasks. Similarly, a language model trained on billions of words understands grammar, facts, and reasoning. This knowledge transfers beautifully to specific tasks like sentiment analysis or question answering. Transfer learning is why modern AI is so effective and accessible. LoRA, or low-rank adaptation, is a revolutionary technique for parameter-efficient fine-tuning. Instead of updating billions of parameters, LoRA adds small adapter matrices to each layer. These adapters have far fewer parameters, sometimes just 0.1% of the original model. The brilliant insight is that the changes needed for fine-tuning have low rank, meaning they can be expressed compactly. LoRA enables fine-tuning on consumer hardware and makes it possible to have multiple specialized versions without storing complete copies. Fine-tuning powers countless real-world applications. Companies fine-tune models for customer service, creating chatbots that understand their specific products and policies. Medical institutions fine-tune models on clinical notes to assist doctors. Legal firms adapt models to understand case law and contracts. Content creators use fine-tuning for writing in specific styles. Developers fine-tune code models for their frameworks and libraries. The possibilities are endless, limited only by imagination and data. Let's discuss best practices for successful fine-tuning. First, start with a good pre-trained model that's relevant to your domain. Second, ensure your training data is high quality, not just large quantity. Third, use appropriate learning rates typically much smaller than pre-training. Fourth, monitor for overfitting by using validation sets. Fifth, consider parameter-efficient methods like LoRA for resource efficiency. Avoid common pitfalls like using too little data, training for too long, or forgetting to evaluate on held-out test sets. We've journeyed deep inside a model to understand how fine-tuning actually works. From the mathematics of gradient descent to the elegance of transfer learning, from backpropagation to parameter-efficient methods like LoRA, fine-tuning is the bridge between general-purpose AI and specialized practical applications. It's what makes modern AI both powerful and accessible. As these techniques continue to evolve, fine-tuning will remain fundamental to adapting AI to solve real-world problems. Thank you for joining me on this deep dive into the mechanics of machine learning.